To truly optimize Apache Spark, writing efficient queries is only half the battle. You have to map the exact physical physics of how your executor memory is allocated and consumed. When a Spark job runs, it distributes work across a massive cluster of machines. But to control performance, we have to look inside a single node and isolate an individual Spark executor container. Even if you are writing your Spark code in Python using PySpark, you are still interacting with a system built primarily on Scala and Java. This means your code ultimately executes inside a Java virtual machine, or JVM. This JVM acts as a rigid boundary that dictates the physical limits of almost every operation your Spark job performs. If you want to prevent silent performance degradation, you must construct a strict mathematical map of the space inside this boundary, specifically the JVM on-heap space. Without knowing the exact dimensions and the dynamic rules governing this container, you cannot guarantee how your data is actually processed. Let's build this map from the ground up. Assume you configure your cluster with a spark.executor.memory setting of exactly 10 gigabytes. A common assumption is that 10 gigabytes is the total amount of RAM requested from a cluster manager like Yarn, the system responsible for assigning resources across the network. That assumption is incorrect. Before any data processing can happen, the cluster manager must allocate a separate block of overhead memory to handle internal system-level operations. Spark uses a strict formula for this overhead. It requests the maximum of either 384 megabytes or 10% of your configured executor memory. This 3D diagram shows the 10 gigabyte JVM allocation. 10% of 10 gigabytes is 1 gigabyte. A distinct 1 gigabyte block of overhead is therefore required. As a result, the total memory requested from the cluster manager is 11 gigabytes. With the overhead accounted for, we can look strictly inside the 10 gigabyte JVM on heap space to begin partitioning the processing areas. Spark immediately slices off and reserves exactly 300 megabytes at the base of this container, exclusively for internal system objects. The remaining space is governed by a parameter called spark.memory.fraction. This determines the size of your core processing area, known as unified memory. Applying this 60% default rule to our 10 gigabyte configuration carves out a 6 gigabyte chunk dedicated to unified memory. Subtract the 300 megabytes of reserved space from the remaining 4 gigabytes, and 3.7 gigabytes becomes your user memory. User memory strictly stores the user-defined data structures, dictionaries, and custom functions you write into your application. Now, focus entirely on the 6 gigabyte unified memory block. This is where the heaviest computational lifting occurs. This space is subdivided by another parameter, spark.memory.storage-fraction, which has a default value of 0.5. This cuts the 6 gigabyte block right down the middle. You get 3 gigabytes of execution memory and 3 gigabytes of storage memory. Execution memory provides the physical workspace for your joins, shuffles, aggregations, and sorts. Storage memory handles the caching of your data frames and stores any broadcast variables, data distributed to all nodes to speed up lookups. By mapping these fractions, you can calculate the exact memory ceiling for complex joins versus cached data long before you ever submit the job. In Spark versions prior to 1.6, the boundary between execution and storage was a rigid wall. If one side filled up, it couldn't access the other's empty space, causing severe memory starvation. Modern Spark solves this with the unified memory slider. This diagram illustrates a dynamic boundary that replaced the rigid wall. Rule 1. If execution requires more space, it can freely algorithm, destroying the oldest cached blocks to manufacture the space execution requires. Rule 3 introduces an asymmetry. If storage fills up and needs more space for caching, it absolutely cannot push into an occupied execution space. This restriction exists because mathematical operations like joins and shuffles are strictly prioritized. The system protects them to ensure the job actually reaches completion. Therefore, when storage is completely full and needs to cache new objects, it has only one option. It must evict its own older blocks via the LRU algorithm. This mechanic exposes a common engineering flaw, aggressively caching data frames that will only be used once. When you cache a single-use data frame, you rapidly fill the storage memory. This forces continuous LRU evictions, pushing out data that actually needs to be reused just to make room for data that will never be queried again. Arbitrary caching degrades performance. Because of the asymmetric rules of unified memory, you cannibalize your own cached storage to protect the execution tasks. Now consider the extreme scenario. Heavy, sustained processing saturates the entire 10 GB on-heap memory allocation. When this JVM container hits 100% capacity, its built-in defense mechanism takes over, the garbage collection, or GC, cycle. A garbage collection pause forcefully halts all active program operations. The JVM freezes execution while it searches for and clears out dead, unreferenced objects to reclaim space. In a high-throughput data environment, these frequent pauses accumulate, creating severe processing latency and acting as a hard bottleneck on your pipeline. To bypass this bottleneck, engineers can enable a specific configuration, spark.memory.offheap.enabled. Off-heap memory is allocated directly to the host operating system. As this visual demonstrates, it exists completely outside the glowing JVM boundary. The primary advantage is uninterrupted processing. Because this data sits outside the JVM, it completely evades the garbage collection cycles. Furthermore, utilizing off-heap memory is orders of magnitude faster than the default fallback behavior of spilling overflow data to a physical hard disk. But there is a strict trade-off. Off-heap usage requires the developer to manually manage memory allocation and deallocation. If you miscalculate, you risk catastrophic memory leaks that will crash the node. Mastering distributed computation means calculating the precise geometric constraints of your on-heap partitions first, and strategically escaping the JVM only when your architecture absolutely demands it.